So again, here is the Stillwater complex. It has a strike length of about 45 kilometers and a maximum exposed thickness of about 6.5 kilometers.
Sorry, Chris, could you switch to the laser pointer?
Yep, just did.
Perfect, thanks.
All right, and I'm going to be focused on the JM Reef, which is located down here in the olivine bearing zone 1 of the Lower Banded series. That's about 600 meters above the contact with the ultramafic rocks, the base of the complex. So typical reef sulfide mineralization looks like this, where we have a sulfide assemblage that's composed of pentlandite, chalcopyrite, and pyrrhotite. This is a rock, an olivine cumulate with a fair bit of intercumulus plagioclase, and it has about 1.5 volume% sulfide, which is pretty typical for the reef. One of the very unique things about the JM Reef is that the estimated composition of the immiscible sulfide liquid has very high platinum group element concentrations. So this is a figure that was taken from Barnes Elements article showing various magmatic sulfide deposits around the world. And we added our JM Reef data, and it plots way up here, pretty close to where the Platinova Reef is located, which is another incredibly high tenor sulfide deposit. And there's been a few proposed explanations for why this might be. One idea is that the sulfides have been upgraded by introducing sulfur undersaturated magmas, which are interacting with resident sulfide liquid and imparting their metal concentrations, their chalcophile metal concentrations. So you end up with low sulfur volumes, low sulfide volumes, and very high metal concentrations in your sulfides. Another possibility is that we've lost sulfur after the magmatic stage due to hydrothermal fluids, perhaps the same fluids that have caused a lot of these cumulates to be altered and serpentinized. And then a final option is that maybe we don't have to overcome anything in order to upgrade our sulfides to the point that we see in the JM Reef. And that could be because new experimentally derived partition coefficients for the PGEs have very, very big partition coefficients. So we're talking, you know, for platinum and palladium, maybe ranges in the millions. And so for the purposes of all the modeling that I did in this presentation, I started with an initial PGE concentration of 10 ppb, platinum and palladium, and used a partition coefficient between the sulfide and silicate liquids of 1 million. So the question that we want to address is, does the composition of the reef vary from one part of the mine, the Stillwater mine area, to another? So to do this, we have a big data set. The Stillwater mine turned over their 30 years of assays, which includes more than 60,000 individual samples. It also includes a composited database where they took the width-weighted average, horizontal width-weighted average, and picked a value that would represent the reef in that drill hole. And then in the East Boulder mine, we have about 2,000 assays. So the East Boulder is located in the far west of the complex. And we have 2,000 samples from there. And this includes copper, nickel, palladium, platinum, sometimes sulfur, and sometimes iron. Definitely the more recent samples include sulfur after they understood how important sulfur data was. So the JM Reef mineralization is commonly located in what we call the Reef Package, which is this complexly layered interval of anorthosites, troctolites, periddotites, and norites. And the mineralization itself is not bound to any specific lithology, and it's also not always present. So in fact, maybe only 1/3 to 1/2 of some of the intercepts are actually hitting economic PGE mineralization. And the sulfides can also be found in the footwall. So for example, here, this isn't typically what we would consider to be Reef Package. We're down in gabbronorite, but we're actually hitting some sulfide mineralization associated with PGEs. And none of the economic mineralization is located above the hanging wall contact to the reef. And this is a textural discontinuity that the miners have recognized marks the top of the mineralized zone. And again, that's not bound to any lithology either, but it's always present, even when the mineralization is not. So through all of this mining, 30 years of drilling, they've very well located the reef, and we now can see that the reef isn't entirely a planar surface. Often the western part of the Stillwater, or the eastern part of the Stillwater mine, it's fairly planar, but we hit this Dow Meadow depression zone, and it's actually a bit of a kinked zone, and the dip angle changes by about 10 degrees going further to the west. The places that are missing here, these are mafic intrusions that are cutting through the jam reef. So what we did is we took the assay database and we broke it up into mine blocks. And these blocks were either historically used by the miners, or they reflect some geologic features. So for example, in this portion of the mine, the entire package of gabbronorite zone 1 rocks is missing. So our footwall is much thinner. And so that's why we've broken this into one particular area. And you can see that the footwall changes considerably as we move along strike. The thickness of the footwall changes, and also the lithologies present in the footwall change. So we took our mine blocks and we just plotted some box and whisker plots and compared the means using Tukey-Kramer, honestly significant difference test. And we found that they are statistically significantly different for both copper and palladium and platinum. I'm only showing platinum here. But this is a connecting letters report, which is a way to summarize looking at the differences in the means of the populations. So any block that isn't connected by the same letter means that it's statistically different. So we can see that as we move from the East Boulder mine, which is in the far west of the complex again, it has the lowest PGE concentrations in 100% sulfide, and that increases as we move towards the eastern part of the mine. And next we plotted up some R factor curves for each of our mine blocks. The ellipses here includes 90% of the data for each mine block. In this case, it's the East Boulder mine, which has a pretty tight cluster. And then the blue line is showing the entire population for all of the mine blocks. You can see that this is a whole rock plot. So this is palladium versus copper palladium ratio. This is convenient because we don't need to have any sulfur data. And these percents refer to the volume percent of sulfide that's present in the whole rock composition. So most of our data is plotting at around just over 1% sulfide in the rock, which is what we observe in the field, and equilibrating at an R factor of about 50,000 to 100,000 for the East Boulder mine. If we look at the other mine blocks, we see that their R factors are much higher, and the populations start to drift down on our curves, and we get these very, very extreme R factors, 500,000, 1 million. Some of the samples are falling even beyond that. And so, go to the next slide. So ultimately, to answer the first question, yes, the composition of the reef does vary at the scale of the mine, the kilometer scale. And in general, the reef is fairly homogeneous, but in greater detail, we do see regions that have higher sulfide concentration or PGE concentrations in the sulfide. And this could be an R factor effect, where some of the sulfides have equilibrated with more silicate melt. This is particularly true in the areas near the Dow Meadow depression zone, that bumpy surface that I showed. It's also more or less in the proximity of the area where we see the thickest chromatite seams in the peridotite zone. So the question is this closer to the feeder to the complex? Is that why we're seeing more silicate interaction with the sulfides? Is that also why we have more chromite in those areas lower down in the complex? And then we also have to address this question of the anomalies and why are we seeing such high R factors predicted for some samples. So there's a couple of reasons that this might be. One is that the reef is very nuggety. We get very large centimeter size platinum group minerals in some places. In others, there's lots of nano nuggets as well. So if you were drilling and assaying and you happen to miss or hit one of these big PGMs, you're going to either over or underestimate the amount of platinum group elements are in your sulfides. Again, the sulfur loss, if we've lost sulfur, but we haven't lost any metal concentration, then when we normalize to 100% sulfide, we're accounting for too much metal and too little sulfide from what was in the original immiscible sulfide liquid. And as Caleb showed, and I'll show a couple images as well, the Reef Package cumulates are variably altered. Some show pretty intense alteration in sort of feathered textures with the silicate minerals, and others show very sharp knife edge contacts. So just to show some flashy pictures of what some of the PGMs from the reef can look like. We've got one in this little vein sort of feature in a gabbronorite, and we've got a couple, or maybe a ½ centimeter size PGM. This was done, an XRF image done by CSIRO. Again, a huge bragite crystal. So if we happen to hit that with our relatively small drill core, we're going to definitely overestimate the amount of PGE that's in that assay. And to address the idea of sulfur loss, what we did is we took the mean value for one of our assays in each mine block population, and we removed 80% of the sulfur by mass and replotted the data on an R factor curve. And we can see that if we used magmatic sulfide upgrading, and so we're dissolving sulfur and adding more metals, we still expect that the R factor curve is going to look something like this. And so this arrow is showing the effect of upgrading at the magmatic stage. This is showing the effect of losing sulfur without upgrading. And this happens to coincide more along the lines of where our contours are drifting off. The same respect, there's been some recent work showing pyrite in the JM reef that is secondary, or they assume is secondary. So if we added some sulfur, we would also drift off in this direction. This reference line is showing the location. It's just a reference. You can compare the data. And we can see that certain areas of the mine show more scatter in their data, but they also appear to have equilibrated at higher R factors than East Boulder, for example. And just to hammer this point home, we also plotted some histograms showing sulfur weight percent in the bulk samples, and the tails are responsible for the scatter in the data. And there's, they make up a pretty small portion of the total population, and so this isn't a major effect. We still think that R factor is the dominant effect controlling the tenors of the sulfides, but we do see that the low sulfur concentration samples are the ones that are drifting off in this direction, and the ones that are high sulfur are drifting off in the opposite direction. And texturally, we see lots of evidence for, thank you. We see lots of evidence for sulfur loss as well. Again, just talking about those feathered textures between the sulfides and the silicate minerals, looking at this phase map, seeing lots of carbonates and quartz right along the boundary of the sulfide mineralization. In this is a fine-grained anorthosite, and also lots of clinozoisite, and then we see our PGMs, platinum tellurides. In the serpentine or serpentinized rocks, the olivine-rich rocks, we also see these really unhappy-looking magmatic sulfides with lots of magnetite rimming them. This could be due to some of the volume increase during serpentinization, where we're actually breaking apart the sulfides and then they're being infilled by magnetite. And so, in conclusion, we definitely see that the composition of the reef varies at the kilometer scale. It's variably enriched, probably at the magmatic stage, and some of the anomalies can be explained by the hydrothermal effects of alteration, removing or adding sulfur, and also by the nugget effect. And dissolution upgrading at the magmatic stage isn't really necessary to explain the tenors that we observe in the reef, And even if it is occurring, it's hard to prove because we don't really preserve any sort of texture or chemical evidence. And if you're interested in learning more, we have a couple upcoming papers coming out in economic geology. One that tells more of this story of the JM Reef, and then the other one is more focused on this magmatic upgrading of sulfides. And here are my acknowledgements. Thanks.